Now, I will tell you about inventory control, an issue that concerns business through an example. This is a spatial optimization problem, and you won't find it in calculus books for engineers. Let's look at the following example. A multimedia company anticipates that there will be a demand for 20,000 copies of certain DVD during the next year. It costs the company 50 cents to store a DVD for 1 year. Each time it must make additional DVDs. It costs $200 to set up the equipment. How many DVDs should the company make during each production run to minimize its total storage and setup cost? From the question sentences, we can understand this optimization problem to minimize its total storage and setup cost. So, this type of the problem is called an inventory control problem. One of the basic assumptions made in such problem is that the demand is uniform. For example, if there are 250 working days in a year, then the daily demand would be 20,000 over 250, which is 80 DVDs. So demand is uniform. The company could decide to produce all 20,000 DVDs at the beginning of the year. This would certainly minimize the setup cost, but would result in very large storage cost. At the other extreme case, the company could produce 80 DVDs each day. This would minimize the storage cost, but would result in very large setup cost. Let's compare these two situations quickly. In the first situation, the company could decide to produce all one at the one day. So one times they pay setup cost for the setup, but for the storage, company 50% storage DVD for 1 year. Okay, actually, each day storage is a bit different. I mean, first day, it cost the company 50 cents to store a DVD for 1 year. So we have a 20,000 cost for the first day. And in the second day, we have 250 less than that one. Not 180 less than, sorry. So 90,000. We should subtract 18. 920, okay. 90,920. It's storage for the storage. So for the third day, the storage is 9, 8, 60, etc. So it continue by this way. For the 30, 60, actually we assume the days 250, not 365, because I found the 18 according to the work day. So by dividing 20,000 to the 250, we find the 80 value. Okay, so it continues by this way. So 250 days, 249 days, there are 80 DVDs. So thusly there is no DVD. So the storage cost is very big in this situation. In the second case, always we pay the setup. Okay, there is no storage, but in the first day, by spending $200, storage is zero because 18 DVD produced and sold out all of them, so zero. In the second day, again by paying the $80 for setup, 80 product produced and sold out. Actually, here we can emphasize. Okay. So this is decrease that value less than 18. So less than 18. So this is the that value, etc. So in the second case, this is the first case. This is the second case. We pay the money for the storage. Sorry, for the setup. However, between these two extremes is the optimal solution that will minimize the total storage, okay, at the setup cost. In the first case, setup cost is minimum, but storage cost, the setup cost is minimum, but storage cost is maximum. In the second case, setup cost is maximum, storage cost is zero, storage cost is zero, so minimum, but totally this is not the minimum. Okay, so we focused on the total one. So let's solve. Let X denote the number of the DVD. Number of DVDs manufactured during each production run. Okay, manufactured during each production run, and y represent the number of the production run. Number of production. It is easy to see that the total setup cost for year is 200 times y, because it's the number of the production run. Okay, so setup cost, the setup cost is 200y. Okay, here in the second case, for example, the setup cost 200 times 250, storage cost is 0. In the first case, the setup cost is 200, okay, times 1. Actually, this is 200. So this is 200y. But what is the total storage cost? This is a bit difficult. Actually, here I could not say anything for you. Now I will explain. If the demand is uniform, we assume at the beginning, then the number of DVD in storage between the production runs will decrease from X to 0. For example, if you produce 20,000, this is decrease 0. But in this setup, if you produce X DVD, for example, 1,000, okay, let's assume we set up 20 times. I don't know what's the optimal one, but if we set up 20 times, each setup, we should produce the 1,000. So if X is 1,000, it becomes 0 after 10 days. Not 10 days. 100 days, and more than 120 days, for example. Or etc. So the average number in storage each day is X over 2. This result can be illustrated as the following way. This is the production run. Okay, let's write here number of the production run. Okay, so X is the number of the number of DVD manufactured during each production. So for the first production, okay, this is the first production. We produced X DVDs, so it became 0. So here we don't have any production. This is 0. So we need the second times to produce DVD players. So again we will produce the X item. So it's X item is produced, manufactured. Then again at the same day, it will be 0. And we produce third times X. And it continue by that way. Fourth times, fifth times, etc. So average number is the storage is X over 2. So this is the average number. In storage. Why? Because it decreases linearly. So half of that value is the average number. Since it costs 50 cents to store a DVD for 1 year, the total storage cost according to average value is 0.5 times X over 2. Okay, so the total storage cost is 50 cents times X over 2. Okay, this is decreasing, that's right. Sometimes in the storage we have X item, sometimes we have 0 item, sometimes we have X plus 8 item, or I don't know, X plus 10 item, etc. But during the whole period, whole year, this is X over 2. Average is X over 2. Okay. Then the total cost is setup cost plus storage cost. So this is 200 times Y plus 0.25 times X. As you see, again, we have a two variable. But we have a constraint. What is our constraint? Our aim is to produce 20,000 copies of the certificated DVD. So in order to write the total cost C as a function of the one variable, we must, okay, this is the cost function total cost C, okay, this is the C here. It has a two variable X and Y, but we should write it as a one variable function. We must find a relation between X and Y. If the company produce X DVDs in each of the Y production runs, then the total number of the DVD is X times Y, which is 20,000. So this implies Y equals 20,000 over X. Now we can set up our optimization problem. Actually, mathematical optimization problem, we should minimize the cost. 200Y plus 0.25 times X subject to 200,000 over X. Sorry, not this one. X times Y equals 20,000. But here we have a two variable. So from this problem, we can create our one variable function. This is cost function, okay? Okay, let's know C of X, Y. So as a one variable function, cost function equals, instead of the Y, I will write the 20,000 over X. So 200 times 20,000 over X plus 0.25 times X. So cost is 5 billion over x plus 0.25 times x. This is the cost function, okay? So we complete the step 1. This is step 1. So in step 2, we should find the critical point. So derivative of the c with respect to x is derivative of 1 over x minus 1 over x squared. So minus 4 billion over x squared plus derivative of 0.25x is 0.25. So for the critical point or critical number, as your textbook says, c bar of x equals 0 or c bar is undefinite actually, okay? So c bar of x equals 0 implies minus 4 billion over x squared plus 0.25 equals 0. So this implies on the other side, okay, so x squared equals 1 billion for 4 million over 0.25. This is 1 over 4. So square root of the x is 16. So 4,000 or minus 4,000. But it is not possible. Minus 4,000, not possible because demand is positive. Okay. Okay. So this is most probably absolute minimum value, but we should prove that this is minimum or not. Maybe you can make the sign chart. You can use the second derivative test. Does not matter. Okay. So let's make the sign chart quickly. But also we have another critical point. The 0 is the critical point. Okay. So c bar x is undefinite for x equals 0. So 0 and the 4,000 is critical point, but 0 is the end point also. So x change between 0 and maybe it can be go to infinite. There is no problem. So c bar x total cost here it is undefinite at the point 4,000, that is 0. So let's calculate, for example, x equals 10. Clearly c bar is negative. Okay, from here, if x is 10, this 0 goes, so this is negative. So negative, positive. So function c bar function, our function, sorry, cost function, not c bar, decrease, increase. So this is local minimum. At the point 0, you can calculate the c of x. At the point 0, c of x is also undefinite, okay? It's not in the domain of the c of x. But again, when x approaches 0 from right side, because x is positive, this is goes to plus infinity, you can observe. So from plus infinity, by decreasing, go to the point when x equals 4,000, and after when x equals 4,000, it goes to infinity. By increasing, you can see the this equation. When x goes to infinity, it goes to infinity, it goes to 0, so it goes to infinity again. So this is infinity. So what we know, function starts for some part here, decrease, and at the point 4,000 go to the turn backs and go to infinity again. Or by using second derivative test. So this local minimum is absolute minimum. By using second derivative test, also you can give the response, second derivative test. So for second derivative test, you should calculate the second derivative of the c. What is second derivative of the c? From here, you can calculate minus 2 x cube. 1 over x cube. Minus 2 times 1 over x cube. So this is 0. So minus plus 2 times 4 billion over x cube. So at the point 4000, this is clearly positive. 400 cube. So this is positive. So this means C takes the minimum value or local minimum value. So this is absolute, we show that. Local minimum value at x equals 400. This is the alternative way, okay? So let's write. This is first way. This is second way to say it is a absolute minimum. Actually, in the second way, just you say the local minimum. By making observation at the endpoints, you can decide. This is either absolute minimum or absolute maximum. In the step 2, we should... actually, we complete the step 2 after find the critical point, okay? So here, find the critical point is the step 2. So this discussion is step 3. And let's turn back the question and give the response for the whole question according to this information. How many DVDs should produce? How many DVDs should the company make during each production run to minimize this total cost and setup cost? Okay, so the company will minimize its total cost by making 4,000 DVDs. Okay, so let's write the company will minimize its total cost by making 4,000 DVDs. How many times it is set up? Y is, let's look to y. 20,000 over x, so x is 4,000, so 5. So DVDs 5 times. 5 times during the year.